So they wrote this paper showing or presenting their empirical experience that sort of root mean square error and sort of top-end ranking performance can diverge quite a bit. And the point here again is that yes, you can pick some loss function you want to optimize, but it actually is important to think about the final goal of what you're trying to solve and how you measure it. And that has an impact on sort of picking good models and thinking about sort of what good prediction is. So this comes up a lot. Lots of companies think a lot about making good recommendations, good predictions in general. So I put a few of the top companies in sort of machine learning recommendation systems, but you can plug in almost any company at this stage, and you're thinking about various ways of doing machine learning and recommendation systems. Okay, so hopefully with all these examples, I convinced you that the way that you choose to measure has a large impact on what your model does in the real world. In particular, again, how you compare different models and what you end up picking, or if you're able to, what you actually optimize if you're optimizing a model. And so what I'm going to go over today are two sets of results. The first is the question of giving a metric, potentially one that's complex. How can we construct classifiers that can optimize potentially complex metrics? So simple things are weighted. More complex things might be sort of complex nonlinear functions of the confusion matrix. And on the second part, very briefly, I'm going to outline even more recent work. We've been trying to answer the question of how do I pick a good metric for a particular problem. And so we'll talk about one approach to try to answer this. We think very clearly that this is not the only way to think about the problem, but it seems like a reasonable way to approach the problem. Now I'll talk a bit about what we've done in this direction. Okay, so I tried my best to channel current web spam. So if you're on the web and you don't have a pop-up blocker, you might often see some version of one simple trick to solve some problems. So the title of the section is One Simple Trick, and it's going to be a reweighting strategy that one can use for optimizing complex metrics. Okay, so beyond binary classification, the idea of measuring confusion extends very naturally. So if I have more than two classes, I can again look at all pairs of predictions and ground truth. So if I have k classes, for instance, I can have all pairs of predictions and ground truth for all those k classes and look at, again, the average number of errors I make on some data set or on some population. If I have an actual, if I can conceive of a generating distribution, all kinds of errors that I can make for a particular problem. And I can formalize this as now a confusion matrix is no longer a 2x2 matrix, is now a k by k matrix for all sort of pairs of different kinds of predictions and ground truth that I can have. And from there, you can again generalize accuracy. So the standard one simple way to write down accuracy is, again, just like before, it's a sum over the diagonal, though now the diagonal is size k as opposed to just a single element. The same exact thing as before. You can also write it as, so this notation here is the matrix inner product between the identity matrix and C, which is my confusion matrix. Again, just summing the diagonal of the confusion. Okay, so if I wanted to solve a standard prediction problem, as we've heard about several times, typically what you do is you come up with some model. We usually formalize or think about this model as approximating probability y takes a certain label. And so there are lots of examples: logistic regression, random forest, deep neural networks, roughly all built to hopefully solve the same kind of problem. And then after that, what you will do is look for the label that has the highest score. And this label you think of as sort of the most likely class label, and then you use this for your prediction. So it's a standard strategy. What I'm going to talk about and suggest today is a slightly modified strategy. So if my metric in this simple case is a linear weighted sum of the confusion matrix. So now remember in the standard accuracy case, this was identity. But more generally, this could be an arbitrary sort of matrix. What I'm going to suggest that you do is, instead of picking just the most likely class, you first do the same strategy of learning some regression model, or classification model, I'm sorry, logistic regression, random forest, DNN, whatever. And then after that, what you choose is not the label with the highest score, but actually the label with some weighted highest score, where the weight comes from this weighting matrix at the beginning. So there are various ways to think about this. You can think about this from a decision theoretic point of view as sort of the best decision you can make out of k choices if you have these weights. You can just, it's actually a fairly straightforward sort of solution to work out if you write down the problem in terms of what should your prediction be in terms of if you have a certain weighted metric. I mentioned this, so even though it's trivial, I mentioned this because in most cases, even when given sort of a particular weighted metric, most people or most work that you'll see just directly just focuses on learning models that do well for accuracy and don't reason about the particular metric that you're interested in for your task and how to modify your model to do well in that particular task. And that's most of what I'm trying to motivate today. Okay, so we tried a little bit of an experiment to see what gain would you have if I actually went ahead. So I'm given a classification problem. Should you bother optimizing this weighted metric, or should you? So I'm given a classification problem with a particular weighted metric. So I have some measure of performance given to you. Should you bother optimizing this weighted metric, or should you just go ahead and do the standard strategy of picking the most likely class? Again, the setup is I have a weighted metric that comes with my problem that I've somehow decided this is the way I want to measure what a good classifier is. And I'm asking, in my choosing different classifiers and optimizing classifiers, am I going to optimize with respect to this thing that I care about, or am I just going to optimize the standard way of picking the most likely class? And this simple experiment, we just did this with random data. So use a simple exponential generative model. The two constants that are interesting are D1 and D2. D1 roughly is capturing how skewed the different classes are. So if D1 is large, then roughly all the classes look roughly uniform in terms of the effective probability of each label. If D2 is large, then it means that in your weighting matrix, you're weighing what one class is sort of much more important than the others. And we're playing with these two constants to see what effect that it might have in terms of prediction. And what I'm going to show is a graph that is just a ratio of the prediction using this preprocessing rule that I just talked about, or prediction just using the most likely class. And you get what mostly makes sense as a result. So what you see is that if A is really skewed, meaning sort of A has a lot of structure, roughly, or another way to think about it is that you have various importance weights on different classes, then it can have a huge effect in terms of how well you do by optimizing the metric of interest versus how well you do optimizing the generic approach, which is just picking the most likely class. So up to, in our simulated example, up to 5 times better in terms of performance by essentially, again, optimizing the right metric versus optimizing just the generic metric. Here I'm showing the skew. So this roughly boils down to if the classes look somewhat uniform, then it makes a big difference to optimize metrics. If the classes are highly imbalanced, so the probability of a certain class has a huge gap compared to other classes, then it's hard to change that ordering with some weight. So the effect of reweighting your classifier is much, much less than it would be if the classes were sort of similar probabilities for different examples. So that's what we're seeing on the x and y axis. The key takeaway here is, as a general rule in many kinds of problems, optimizing a metric that accounts for the way that you're measuring or you care about measuring your classifiers can have a big impact on how much better you can do in terms of building a good classifier, a good model. And so you can extend this strategy not just for linear weightings, but for more general weighting. So if you recall, I talked about having a metric that was some generic function of the confusion matrix. And the strategy that we're suggesting is super simple. So I take my generic function. I first learn any calibrated classifier, so random forest, logistic regression, whatever you like. And then I reweight my scores based on a certain weight matrix. The difficulty or the challenge here is that this weight matrix, the optimal weight matrix choice is the gradient of the metric, but it's the gradient of the metric at a point that I don't know. So it's the gradient of the metric at the optimal confusion matrix, which is C star, which is C star is arg max VOC. So roughly what this is saying is if I knew the optimal confusion matrix for my problem, I would take the gradient of the loss function at this optimal confusion matrix and use this as my weight. In practice, I'm not going to know this optimal confusion matrix. I have this weird problem where the weight that I need to make a good decision, I don't know it. I don't know it when I start. I'll briefly go over how one can solve this problem, or one approach we've used to solve this problem for binary classification, and I'll defer to papers for how you can solve this problem for more complex classification settings. I also wanted to mention, so we've done this for various kinds of classification problems. So for binary classification, which I just talked about with sort of pairwise classification confusion matrix, but you can also do this for multi-class classification, which I just described as a setting where you have k different classes and making k different predictions. There's a slight variation where we think about multi-label classification. So you're making lots of binary choices simultaneously. And then you can think of multi-output classification where you are making lots of k class choices at the same time. And again, a similar kind of trick follows through, and so we can use the same approaches to solve each of these problems. We also looked at this for recommender systems as a motivating example from before. So here I have items, users and items. I'm interested, each user we observe assigns a rating to a certain item. And I'm interested in for new users figuring out, or users in my system, what other items I should show them. So I'm interested in finding items that have a high score to use as my predictions. One way to formalize this, and how we chose to formalize this, is as a simultaneous multi-class classification problem. So I'm making multi-class classification decisions across lots of different movies at the same time for every user. And you can think about this again as this is the multi-output setting that I talked about earlier, where I'm making lots of k-class decisions at the same time. Okay, and the metric I'm showing at the bottom is an ordinal classification metric, which is trying to essentially, there's an order between the different labels, and it's checking the error that you make, and it's weighing it by how far the two labels are from each other. So if the two labels are far away, then you get a high weight by making that mistake. If the two labels are close to each other, then you have a low penalty for making that mistake. Okay, so we looked at an existing model for solving this problem. It's published in 2011. It was built specifically to solve these kinds of ordinal regression problems. So it builds a probabilistic model focused on this, on solving this problem. So it has sort of ordering built in the model formulation. And what we showed is that even though the model is built to preserve order, if I solve the problem without accounting for, in my decision making, if I just pick the most likely class, I do worse than, again, if I account for the fact that there is this weighting in my metric. So picking the class weighted by how important they are in terms of my final decision. So I want to give some intuition about what this reweighting is trying to do and when and why it works. One way to think about what the reweighting is doing is to reason not about classification, but actually take a step back and think about what's going on in the confusion matrix space. So for folks who are familiar with machine learning, this is effectively like the RLC curve, but then I also drew the inverse RLC curve that you might have seen before. In particular, I'm also exploiting the redundancy in the confusion matrix representation. So I only need two elements to fully describe everything that's going on in the confusion matrix. So you can show that the set of feasible confusion matrices, so if I look over, for a particular problem, if I look over all possible classifiers that I can come up with, I can actually characterize a set of all possible confusion matrices that correspond to various classifiers. And what you can show is that this set is a convex set. It's actually a fairly straightforward proof. And so one thing that follows then is that the optimization of whatever metric you're interested in will depend on sort of the gradient of the loss function and how that interacts with this convex set. And what's interesting and useful for our setting is that if I'm optimizing a monotonic metric, so a metric that is monotonically increasing in the diagonal of the confusion matrix or decreasing in the off-diagonal terms, meaning my metric gets better if I make better decisions or gets worse if I make worse decisions off diagonal of the confusion. You can show that the optimal will be somewhere along the boundary. So the best confusion matrix would be some confusion matrix that's on this boundary of the set of feasible confusion matrices. And what follows then is a couple of things. So we can characterize boundaries of convex sets using support functions. So the support function determined by sort of the normal at that point, which you can think of as sort of the confusion matrix element at that point. And it turns out that the weight that we need is the gradient of the cost function at this, exactly at this point, which is at the boundary of the confusion matrix. So the strategy that you need to come up with is a strategy that helps you figure out what this C star is and use that to determine the weight. What's really interesting about this that we eventually found out is that this characterization is also exhaustive. So this is actually an if and only if type condition. So the if and only if statement is if a metric is optimizable via this linear reweighting, then it must it must have an optimal confusion matrix that lives on the boundary. And the opposite is also true. If the optimal confusion matrix is on the boundary, then the metric is optimizable using this linear weighting. So it essentially tells us the space of all metrics where we can solve them by using this reweighting trick. Those are characterized by this sort of boundary condition. And so this is something that you can apply generally. It has useful statistical properties. In particular, you can show that it's consistent, meaning with large samples, it converges to the Bayes classifier, which we heard about in the morning talk, meaning that's the classifier that you get if I knew the distribution and I actually sort of try to optimize for the best possible classifier for a particular metric. So you can show that this strategy of finding this reweighting matrix and reweighting your classifier based on this matrix gives you a consistent classifier. For the binary classification case, we can say something a little bit stronger. We're still expanding these to sort of more general cases. So in binary classification, your problem gets a lot simpler. So the reweighting matrix boils down to effectively picking a good threshold. So what I need to do is, in a binary problem, I learn a logistic regression model, which again, you can use any of the standard techniques that you like, but we have results for logistic regression with maximum likelihood estimation and sort of kernel approximation for Holder smooth densities. You plug in your estimate of the conditional probability, which tells you a family of classifiers based on where you pick your threshold. And it turns out that this reweighting just boils down to finding the best threshold. This interacts with data in two ways. So you first, the quality of your estimated conditional probability depends on the amount of data that you have. So with finite data, there's some error that comes from sort of having finite data for computing approximate conditional probabilities. And you also pay a cost in terms of maximizing the threshold. So the cost that you pay is because the metric that you're estimating is the metric approximated from finite data. And so there's a gap between the confusion matrix and finite data and the sort of true or population confusion matrix that you would like to actually optimize. And so that gap shows up in estimating the empirical metric and trying to find a good threshold. And so what you can show then is that the estimation rate is bounded by sort of a log factor, order log n over n. For those who are familiar with this literature, you may know that if I was trying to solve a standard binary classification problem to optimize accuracy, the bound in that case is sort of order 1 over n, sorry, not 2. And so one way to think about this is that you pay a log n factor for having to find the threshold, as opposed to knowing the threshold ahead of time, which we know for standard binary classification problems when you're optimizing accuracy. So if I'm optimizing accuracy, I can get, for certain problem settings, as good as an order 1 over n rate. If I, in addition to this, have to find the best threshold because I'm solving sort of complex metrics of some kind, I pay a log n factor on top that you have to account for. Okay. So there's another question that comes from this, so the beginning when I started when we were working on this initial problem, I'd give talks and be super excited about, these are cool results, they're super helpful for, essentially, we can quantify how you should build classifiers for really sort of metrics that were complicated that people were using that sort of didn't know how to quantify or think about good models for. And the question that I always got asked was, well, which metric should I pick out of, like I mentioned, potentially, well, literally infinite, actually, number of metrics. So even if I take linear reweightings, I can pick any arbitrary linear weight. Each linear weight is a different metric. I literally have infinite metrics that I could potentially use. And a reasonable question is, well, which metric should I pick out of all of these metrics? So we have an answer that we think we like, but I would say that this is very much an open problem that a lot of folks in the field are still thinking about. So I should also mention that there's actually not that much work in thinking about which metric to use. So most folks in academia, when they think about optimizing classifiers, just use whatever default metric shows up in the field that they're working in. So almost everyone just focuses on accuracy. If you're working in image classification, you might use top K accuracy, which balances the fact that we don't always get the labels perfectly correct. F1 measure if you're doing information retrieval type problems. Industry is a bit more careful than academia is. So often they'll hire some consultant or economist and who will spend several months or several years trying to think about what the right way to measure sort of good models should be. And you might do a bunch of A/B tests or user surveys and try to use that to come up with a good metric. So the point here is that this is not a trivial problem, and it's not one that's well solved. So what we chose to do and what we think might be a reasonable approach is we formalize this problem in terms of thinking about how an expert might want to pick what a good model is. So our intuition is an expert knows a good model when they see it, but they don't know how to put numbers and actually say this is the metric that I care about that actually quantifies this notion of what a good model is. And so what we want to do is query the expert and ask them questions roughly about the model. And use their answers to come up with what they're, hopefully, assuming they're consistent decision makers, consistent and rational decision makers, are what the metric that they must be optimizing is in order to make those classification preferences, in order to give us those classification preferences. One thing you quickly find out is that people are not really good. If I give you a classifier and I tell you how good is this classifier, give me a number. People are quite bad at that. So very few people can actually do that. Someone in a talk once said that they could do it. And I challenged them, and I was actually quite impressed. Some people can. I cannot, and most people cannot, given sort of a range of classifiers. Just give me numbers for each of these classifiers. Now, if you could do this, then it makes your problem a lot easier, because then I can just interpolate somehow, and this gives me some notion of metric. But however, people are pretty good at pairwise comparison. So if I give you two models, you can tell me what you prefer between the two. Roughly you look at what properties each of those models might be capturing, have some intuitive notion of sort of what's good or bad between the different models, and you can tell me pairwise preferences. And people are reasonably pretty good at this. Now, people also get bored quite quickly. So if I ask someone a million questions in order to pinpoint sort of their notion of preference, you're not going to get very far before you end up sort of boring people and they're no longer interested in solving this problem. So it's important that we can solve this problem as quickly as possible. So the speed of sort of how many queries that you ask, in this case the oracle or the expert, matters. So you want to do it as quickly as you can. And so the way that we solve this problem is to essentially exploit similar geometric properties as we had talked about before. So because the space of classifiers is this convex set, for certain kinds of metrics, in particular things like linear or reweighting metrics, you can show that you only need to search sort of a one-dimensional subset of this space. And in particular, you can just focus on searching the boundary. And finding the best point on the boundary tells you everything you need to know about sort of the best metric that whoever you're querying is interested in. So the idea then is, since we know that the optimal is only on this boundary, we can just query along this boundary, which is roughly parameterized by some kind of angle. Or we can reparameterize in terms of some kind of angle. So we boil this down to a simple binary search. So you can think about this as taking, so sort of this line all the way from here to here and stretching it out. And what I do is I ask, do you prefer this classifier to that classifier, those pairs? And from there I can tell sort of, by doing these binary queries between sort of pairs of classifiers, I can tell, I can convert that into a binary search algorithm that roughly tries to find out, by a sequence of binary queries, which point in this space must be the maximal point. This depends on the fact that for many metrics we can show that they're essentially, you can show that for many metrics under fairly weak conditions, they're unimodal, meaning that there is a unique sort of single angle that's best in terms of what's optimal. So for instance, for a linear metric, you can show that there is a unique point where you can show that there's a unique point that maximizes sort of the best possible linear metric in this space. And so again, you can convert this to a binary search problem. It does two things at the same time. It finds C star, which is the optimal confusion matrix, and it also tells you the gradient by exploiting the fact that there's a convex set, and we can sort of work out. So roughly by figuring out, this is supposed to be a tangent. The tangent, we can fairly easily also figure out the tangent, by figuring out the normal, we can also figure out the tangent geometrically. Based on both of these, I can tell you what the metric is by pinpointing sort of the right angle along all the different angles that I could search through. So this is useful. We can show some interesting things in this case. So in the linear case, things are the easiest. We can show that we can recover the linear metric with some epsilon error. So depending on the tolerance that you're interested in. If you're interested in the tolerance epsilon, we can elicit the metric using order log 1 over epsilon queries. And we can also show that this is, you can't do better under sort of, without making stronger assumptions. So this also matches the lower bound for this kind of problem, which roughly boils down to sort of how hard is it to find the maximum of a unimodal function using binary search. So sort of fairly straightforward. And in practice, we started to analyze this a lot more, but we have some theoretical results trying to characterize what happens if I add different kinds of noise. So finite sample noise, noise from experts not being able to tell us exactly what preferences. So giving us incorrect comparisons sometimes, and seeing how bad this is in terms of how bad the elicitation problem is. And we can roughly characterize it, and our results show that this binary search algorithm is fairly robust. So we can make small modifications to make this robust to various kinds of noise and errors. Okay, so if you stayed awake for most of this, we'll hopefully convinced you, or at least intrigued you, that picking the right metric has a big impact on how well your machine learning model works in practice. I've shown two things. So I've shown that we can come up with reweighting strategies, details TBD, that are efficient for optimizing complex metrics. In the binary case, it's super straightforward. It boils down to finding a good threshold. In more complex cases like multi-class and multi-output classification, it's a slightly more involved problem. But again, boils down to finding sort of the right reweighting matrix. And the second part, I talked about reducing metric elicitation for binary classification to a binary search problem, and we showed that we can do this with bounded query complexity, so we can bound how many times I have to ask the expert pairwise comparisons for which classifier they prefer. So we're looking at this a lot more. We think that measurement is important and is at the core of all of empirical research, so beyond even machine learning, thinking about how you measure and how you compare things. But in particular, we're interested in extensions to other kinds of machine learning problems. So we're following up on more complex machine learning beyond binary and multi-class, so ranking and regression, things like that. We're thinking of ways of being even faster, so even faster elicitation by doing something smarter than just pairwise queries. So thinking about things like auctions and other more complex query mechanisms that might actually allow you to elicit the metric even faster. We're very interested in practical implementation, which means thinking very carefully about noise and robustness and other useful properties. And with that, I think I'm mostly in time, so I'm going to end. That's it.